Hi, welcome to Nomenclature Day. Um, on your periodic table, if you would, I need you to copy down your oxidation states. If you forgot what that means, it's the blue numbers you see above the red columns. All right, so your columns are numbered. Are they numbered on that one? No. Um, so just look where it is. So above the first two columns, it's +1 and +2. Ignore the dip. Then the very first column after the dip, which is group 13, is +3. Skip a column, -3, -2, -1. Nothing above the last column. If you remember, those predicted charges should be written on every periodic table you ever receive automatically because they have many uses. I can discuss the origin of them. I don't have time today because we're not talking about their origin. But if you remember, it had to do with the octet rule. As they gain or lose valence electrons to get either 8 or 0, that's the predicted charges after that change. But anyway, they're a big deal for our nomenclature, as I'm sure you remember from last year. Because as you were copying down your slides, hopefully the 3 naming systems really came back to your mind because we have done everything that we're doing. This lecture is 100% review. Those of you at home, you should have access to your notes, of course. So make sure you are following along. All right. Wait for it right now. Oh, well. Another thing I'd like to remind you of is that there's an invisible zigzag right here. And what that invisible zigzag does with this being, this is boron right here, and here's aluminum. All right, just so you kind of have an idea on where it exists. But if you remember, it actually does a separation of types of elements. Everything over there was a non-metal, while everything over here except hydrogen was metal. But of course, for our naming of compounds, that's really important to know that the majority of the table is non-metal, right? There's not very many elements over there. And then there's a ton of metals, right? Mine isn't drawn to scale, obviously. But just remember that hydrogen up here is non-metal. He's the only exception to what I just drew in brown. So with that in mind, we've got 3 different types of compounds that you were trained to name last year, and it's going to stay equally important this year. So let's tear back through them. Of the assignments on Canvas, this is the longest one in the unit in terms of number of questions. But I just want to remind you that when you're doing nomenclature problems and you kind of get on a roll, it goes really fast. I mean, if you're good at it, which I hope you can remember that you can be good at it. But I think there's 39 questions. That shouldn't intimidate you because you don't really have to think once you get rolling. But let's start with covalent. Ready? By definition, covalent is a nonmetal bonded to a nonmetal. So as long as you know where the nonmetal lives on the table, then it's easy to identify. All right, so it's going to be 2 elements from over here forced together into a compound. The naming of this is very straightforward. It's the ionics at the end that have a bunch of stupid rules. But this one's really straightforward. But just like last year, the prefixes are not given to you. So monoditride, tetrapentahexaheptaoctanonadeca is something that you need to be able to do while keeping in mind that you know a lot of those, right? A tricycle has 3 wheels, an octagon has 8 sides. So it's not built to be confusing. But with those prefixes in front of you, let's practice. All right. F2N5. I know it's covalent because fluorine and nitrogen are both in the non-metal area. So all I'm going to do is name the elements and apply prefixes. F is pronounced fluorine. N is pronounced, it's nitrogen. What do we do to the second word? We change its suffix. So I want to also remind you that the Ides live over here in non-metal land. All right, so it's referring to the second word, but anytime we deal with an Ide showing up, it's going to be referring to a non-metal in some context. So the F is fluorine, the N is nitride because it was the second word, and then I just apply the prefixes. The prefix for 2 is di from the opening slide. The prefix for 5 is penta. And we now have difluorine pentanitride as the name. Make sure you interrupt me if you don't understand something. Your silence makes me think you're with me. All right, SCl8. Bless you. You allergic to covalent?
Yes.
Oh, and you're sitting closest to this, and you spoke really loud. I know it's covalent because both sulfur and chlorine are nonmetals. Yeah. So make sure, remember, that's the most important part, is identifying it, because if you don't do that and realize it's covalent, then you're going to name it wrong, or you might use one of the other systems. So now I name both elements. S is pronounced sulfur. Chlorine, changing it to ide for the second word, is pronounced fluoride. And since it was covalent, I apply the prefixes. All right, so S is mono. Does anybody, was it on the opening slide, the special rule? There's a lag. No, it's not. So, I should add that. Remember the one side rule for covalence is we never put mono in front of the first word. All right, so there's only one sulfur, but we never put mono in front of the first word. You can put it in front of the second word, but we're not going to call it monosulfur. We're just going to not give it a prefix. So sulfur, and then 8, of course, is octa. Sulfur octachloride. Let's go the other direction on one. All right, tricarbon tetraiodide. Tricarbon tetraiodide. If I give you the names and you have to write the symbols instead, first off, make sure you keep the naming system separate, right? Covalent, acidic, or ionic. But only covalents use these weird prefixes, so it's very clear, very obvious that it's covalent when you see them show up. So now we just have to reverse engineer the formula. So what element do you see in tricarbon? Obviously, and what does tri mean? What element do you see in tetraiodide? Iodine, and what does tetra mean? You try a couple. Translate both of those items to the opposite nomenclature. I'm just going to show you down. All right, hexaphosphorus decaselenide. Let's draw some cards. Just tell me what you wrote. Let's go over to cluster 4, seat 4. Hey, 4-4, what'd you get? Oh, we picked on you recently, right? Yeah. What'd you get? Do y'all agree or disagree? It's perfect, right? And there's no reduction, right? 6 and 10, we don't drop it to 3 and 5. Ionics has a reduction rule. Covalence doesn't. It's one of the fun things that you've got to keep straight in your mind. All right? We need the name of Li2O. Let's go over to cluster 6, seat 2. Hey, 6-2, what'd you get? Dilithium oxide? Anybody get a different answer? Just yell it. Dilithium monoxide. You'd want to put mono, but what if I told you I still haven't heard the right answer? Anybody get another answer? No, don't. Yeah, don't flip. You're thinking ionics, so that's also wrong. Still nobody? All right, so see, I tricked you, and you're my AP kids. I'm not supposed to trick everybody. It's lithium oxide. It's not covalent. Now, that was mean of me because I haven't covered ionic yet, but someone should have at least raised their hand and been like, but sir, lithium's not a non-metal. Because that's a really important distinction, right? We are only doing non-metal to non-metal. Lithium lives over here in metal land, meaning these rules don't apply to this compound, which is the biggest mistake y'all make, is crisscrossing the rules. So, while the monoditris tetras are important, the what the heck am I looking at is way more important. If it's metal to non-metal, it's ionic, which we'll cover soon. Yeah? Let's move on to acids. Okay, so you copy down the acid rules from your slides. Have those acid rules handy in front of you so that you can reference them as I talk. I also gave you a polyatomic sheet. Keep that. Remember, you don't have to memorize. I know it's broken up to like quiz sections. No. You don't have to memorize any of your polyatomic ions. But have it handy. If you at home, get a polyatomic ion sheet. It's the dude that looks like this. All right, those are the rules you should be looking at home. Okay, acids start with H. All right, they are compounds that start with H. If you're given the wordy form, then they have the word acid. That's our big way of knowing what they are. So we're done with non-metal to non-metal. Instead, we have an item starting with H, makes it an acid, or it's got words followed by the word acid. And my purple rules apply. So let's check it out. HBr. I know it's an acid because it starts with H. I know it's not covalent, all right? We're not treating it as covalent because of that H starting it off. So we're not going to do any prefixes. Once you realize it's acidic, your job is to ignore the H and think about the rest of the compound and ask yourself, how would I say this entity? Well, how do you say Br when it's bonded? It's pronounced bromide. All right, now, this is not a part of the answer what I'm writing here. I'm showing you my brain. I'm thinking that Br when bonded is pronounced bromide, and there will be a suffix there for your brain to cling onto, because that suffix is going to activate one of the acid rules from a moment ago. What is the rule for ide? It's hydro blank ic. Hydro. The blank is going to be everything that's not the ide. And ic. following the rule from the previous slide. Add the word acid, and you've done it. Hydrobromic acid is HBr. Let's do another one. Remember, if you're sitting there wishing I was teaching this slower, there's videos linked in an announcement covering all of the nomenclatures. H2CO3 is definitely an acid because it starts with H. Now I'm going to ignore the H and just look at CO3. What is CO3? It's on your polyatomic list. He's carbonate. CO3 is pronounced carbonate, which is just something I'm thinking about. But look at the suffix there. 8. If you haven't found carbonate on your polyatomic list, point it out to the person that has it, or have someone sitting next to you show you where carbonate is. Hey, what's the rule for 8? 8 turns into just ick. It's blank ick. So in the blank, I'm going to put the leftover, then the ick from the previous slide, and you've got carbonic acid. All right, let's do another one, but let's go the other direction. What if I give you the words and you need to write the formula? All right, looks like we're dealing with nitrous acid here.
Good morning, teachers. This is your friendly reminder that you have 2 minutes worth of the possibility of heaven. If you still have the ozone and temperature of the world, please consider it on the frequency. Thank you. Have a great day.
When going the other direction, the moment I see the words, but I see acid, what element do you think of no matter what? Hydrogen. If it's an acid, you know it must start with H. And then our investigation goes to nitrous. Now, again, we're thinking of the rules on the previous slide, and you need to reverse engineer what it was originally. See how it ends in OUS? What does the rule say it was before it ended in OUS? Yeah, it ended in ITE. And you can see that connection on the acid rules. So what I need is nitrite. So go and investigate your polyatomic list. What's the formula for nitrite? Nitrous acid is HNO2. Now, there was a little ionic thing you're supposed to think about right here, and I'll hit this hard in about 5 minutes. But I just want to remind you that when you're building acids, you do have to put our charges into play, our oxidation states. Hydrogen has a charge of 1. Nitrite, that's on your polyatomic list, has a charge of 1. So nothing happens, but you are required to check. We'll get back into that soon if you don't remember how it works, if something does happen. Anyway, you try a couple. Translate both of those into the opposite form of their nomenclature. You can talk to someone sitting near you if you're stuck. H2CrO4 is an acid because it starts with H. Make sure you're going through that part of the thought, right? Because I tricked you on the last slide because you didn't go through that thought for covalence. If you ignore the H, let's go to cluster 6, seat 1. Hey, 6-1. If you ignore the H, how do you pronounce just CrO4 polyatomically? So I gave you the sheet though. So find CrO4. It's on there. Scan till you find it. It's chromate. CrO4 is pronounced chromate. So I'm just thinking about that. But there's the 8, which will activate the 8 rule, which is blank ick. Sounds like blanket. Blank ick. So I'm going to put this in the blank. I can spell. Chrome goes in the blank. I add ick instead of 8, and then acid. Did you get chromic acid? Hydrosulfuric acid. All right, so I know it's going to start with an H because of the word acid. Let's see if somebody can give me a correct answer. Let's go to cluster 6. Wow. I'm only missing one of you in cluster 6. Seat 5, though. I guess 2 of you. I forgot. Aspen, what did you get for hydrosulfuric acid? H2S. Do y'all like that answer? Well. Yeah, that is the answer. There's a lot going on there. Let's talk about it. First off, acid, so it starts with H. Then I look at that word. I investigate it carefully, and what I see is a hydro and an ick. If you go to the previous slide, hydro and ick is connected to ide, and ides are connected just to these elements over here. So it must have been sulfur, original. Sulfide is originally sulfur. So there he is. But then that little ionic thing I haven't totally taught today yet happens, where hydrogen is +1 because he lives there. Sulfur is -2 because he's in that 16th column. And there was a crisscross, which we're about to practice. So if you don't remember the crisscross, you're like, that doesn't make sense. I'm going to explain it fully in a moment. But yeah, H2S is the answer. Of course, Canvas is going to hook you up with some good practice. How are we doing? We're 2/3 of the way through, kind of. Ionic's the one that takes me the longest. Okay. So, you copy down all these rules as reminders. For my ionics, we're dealing with a metal bonding to a nonmetal. So now we've got an element from this side being connected to an element from that side, which activates these rules. Or a polyatomic ion bonding to anything is going to require this look at charges. Remember, it does require reduced values on the crisscross. We'll practice that. This is where parentheses can show up sometimes, but this is the rule. And then you also have Roman numerals you have to mess with. So yeah, ionic was the thing that caused you usually the most issues for nomenclature. But keep in mind that your exam is open note. So one of the things that I have found that students do to make sure they don't mess up the nomenclature questions on this first exam is they just have a ton of examples that they can, like when you are when you're doing the nomenclature assignment, I would work all of it out on a sheet of paper and not throw away that sheet of paper. All right, there's a good chance that there might be some overlay between the 39 problems you have to solve and actual test questions. Maybe the answer would just be there, right? But you could have really good notes for this open note test in addition to what we're about to practice here. So anyway, be ready to look back at this screen as I'm going through these examples. Let's give it a go. All right, we're doing ionic now, which is going to be a metal bonded to a non-metal, or a polyatomic bonded to anything. Lithium nitride. All right, I know it's ionic because lithium is metal and nitrogen's non-metal, right? We just look at their locations on the periodic table. So we're not doing prefixes, right? We're not messing with any of the monodies, tetras, etc. Here we go. Write the symbols first. Lithium is Li. Nitride is just nitrogen. Since it's ionic, I identify oxidation states, which are those predicted charges that you wrote at the beginning of class. Make sure you stop me if you don't know where something comes from. Lithium lives in the +1 column. We don't care about the pluses and minuses, though. Nitrogen lives in the -3 column. What we do is we crisscross these numbers as subscripts, and we reduce them if they can be reduced by each other. So if it was a 2 and a 4, well, a 2 and a 4 can be reduced to a 1 and a 2, right? You could chop them both in half. It doesn't happen here, though. So this 3 will go there. This 1 will go there for a final formula. Lithium nitride. Don't know how to read your faces during this lecture. You do one. Translate radium sulfide. Did you make sure it was ionic? All right. Yeah, radium is in metal land, sulfur's in non-metal land. So yes, no tricks here. So here we go. Radium is Ra. Sulfide is really sulfur. What's radium's oxidation state? Anybody? It's 2. What's sulfur's oxidation state? It's 2, based on their location. So we want to cross the numbers, but they have to be the reduced version. So 2 as a ratio to 2 can be reduced to 1 to 1. All right, so really what a lot of y'all memorized last year is if they're the same number, you just don't do anything, they cancel out. But really, mathematically, they're turning into ones. You're crossing the ones, but we don't show ones. So it's just rouse. Radium sulfide, yeah? All right, let's do the next one together. Aluminum sulfate. Now, sulfate is polyatomic. I liked if that is obvious to you right away, not just from your experience in chemistry last year, but because you did have to memorize them last year. So it's super helpful when you know right away that sulfate is not on the periodic table, that it's on your polyatomic list. So if you were never good at that or you're newer to chemistry than you're supposed to be this year, You need to familiarize yourself with that list. You don't have to memorize any part of it. I'll always give you the information, but your familiarity could harm you if you don't realize that it's there. Okay, but polyatomic bonding is automatically ionic, so let's write the symbols. Aluminum is Al. Sulfate, reading it off of your polyatomic list, is SO4. Everybody's cool with that? Aluminum's oxidation state is 3. Sulfate's oxidation state, also read off the polyatomic list, is, yeah, it's -2. As a ratio, those numbers cannot be reduced. So I'm going to cross the 2 there, and I'm going to cross the 3 there to build my final formula. So aluminum gets the 2. And then here's one of the things that you wrote as a rule on the prior screen. Here it is. If a polyatomic ion is crisscrossed a number greater than 1, add parentheses to the polyatomic ion. You already wrote that down. You just have to be able to read English. All right? See how that number is bigger than 1? See how sulfate is polyatomic from your list? Anytime that happens, you don't change sulfate. It has to stay SO4. But we protect him with parentheses and then cross the number. Aluminum sulfate is Al2SO43. Things start getting exciting. You try one. We'll draw a card this time. All right, so let's have someone just tell me what their answer is. Let's go over to cluster 2 and talk to seat 3. Ooh, Aspen, it somehow found you. Kate, what'd you get? Where did you close the parentheses?
The
Yeah.
O, right there.
And then the
And then
2?
2.
Okay, cool. I just want to make sure we're on the same page. Yeah, that's a perfect answer. So let's talk about why. Now, careful, I do this to you on purpose because these parentheses are harder to see than the previous ones. But I followed the rules I gave you. Strontium is Sr with a charge of +2. Hypochlorite is just ClO with a charge of -1. The 1 crosses and doesn't show up. The 2 crosses and the rule activates. That number's greater than 1, yeah? That number's a polyatomic ion, yeah? Then you need parentheses, just like the rule says. It's easier when there's already a number down there because things just look weird. But you don't have to have a number down. Let's do another one together. Ooh, Roman numerals. Anytime a Roman numeral shows up, you should be happy. These are easier ones because it's less work, even though they intimidate y'all for some reason. Look here. We're doing this one together. You don't have to be thinking right now. I want to remind you. Do you think they can hear me way over there? Oh, I didn't ask y'all permission. Are y'all cool to be on camera? Are you sure? Dang it! You almost ruined my whole video. You want to wave? Wait, get away. Okay, cool. Anyway, the reason that Roman numerals exist is because the transition metals, this area in the middle, these dudes have multiple charges, right? Like lithium's always +1, so he doesn't need a Roman numeral. But cobalt can have 3 different charges. So if cobalt shows up, you don't automatically know what its charge is. You're like, well, which cobalt? There's multiple cobalts, which is the whole point of Roman numerals. Roman numerals are required for most of those transition metals to tell you which species the example is referring to. So, with that said, we've got iron 2 oxide. All right. I know it's ionic because that is a metal and that is a non-metal based on locations, but also only ionics use Roman numerals, so it must be. But anyway, so here we go. Let's same process. Nothing changes. Iron is Fe. Oxide is just O. Iron doesn't have, I mean, iron's here, right? Iron's in this section. So you don't know his charge, but you do. What's his charge? 2. That's what the Roman numeral tells you, and that's the only purpose of a Roman numeral is that moment. So easy. What's oxygen's charge? Yeah, he's in group 16, so 2 also. So what's going to happen here? Yeah, they essentially cancel out. You're crisscrossing a couple ones. Iron 2 oxide has no subscripts. Those of y'all that are bad at chemistry will find a way to make a 2 show up in your answer because you think it has to be there. If it's got a Roman numeral 2, the answer's got to have a 2 in it, right? No, wrong. You do this one. You can ignore the yellow. Just answer that question. If you don't know what Roman numeral that is, ask your neighbor. I know it's ionic because there's a Roman numeral, but there's a polyatomic is bonding. So here we go. Platinum is PT. Arsenate, you should have looked him up on your polyatomic list, is ASO4. Yeah. What's platinum's charge here? Yeah, +4. Keep in mind that they're always positive. Roman numerals are always positive. It doesn't matter for right now. But you wrote down in your slides today that it reminded you. What's arsenate's charge? -3. All right, those numbers, that ratio can't change. 4 to 3 can't be simplified with whole numbers. So we just cross. All right, so platinum gets a 3. And arsenate, a polyatomic ion, gets a 4, a number bigger than 1, which will activate our parentheses. That's a fun one, yeah? Rapidly running out of time, but we've got a few more I want to show you. Yes. You're good. Hey, yeah, well, it's gonna come up one at a time though. It'll be on the video. So the yellow though reminds you, you wrote it down on the slide before this one, that zinc, cadmium, and silver are the three transition metals that do have a constant charge, right? Plus two, plus one, respectively. So it's just, I know it sucks, but it's the way that the universe built the world. So okay, what about going the other direction? I do want to warn y'all, I don't want to speed up me teaching this since I'm making a video, but I am going to finish this slide. So if I get cut off by the bell and you're like, I really wanted to see that last one, I'm going to keep teaching. And it'll be in the video. So you're welcome to go and scrub to the end if you want to. Anyway, check out this next example on going the other way. All right, RB3P. I know it's ionic because metal and non-metal, but it's my opinion that writing the words is a lot easier than writing the formulas because you don't have to do as much thinking through numbers. What I know is that when I'm writing an ionic name, there's always two words. You just need to find those words. Like RB is pronounced rubidium. And P is pronounced, it's phosphorus, but when it's the second element, it's going to get that ending if it's over here. So it's phosphide. And that's it. You're done. Rubidium phosphide. Now, a lot of students are like, well, what about the 3? You didn't do anything with the 3. I know, because it's hidden in that word, right? Phosphorus has a charge of 3, which is why if you went back to that, you would do all the crisscross madness. But going this way, as long as you are on your game, you're not going to mess it up. Let's do another one. Do you feel like you must put your stuff away while I continue? You're welcome to, but try not to overpower me with your sound. BACN. All right. I know it's ionic because we have a polyatomic bonding. So now we'll just, again, find where the names are. And here's where your knowledge of the polyatomic ions can be really helpful. But Ba is pronounced barium, and Cn, if you look, is pronounced cyanide. And that's it. Barium cyanide. Right? That 2 comes from barium's charge, but who cares? I was going to have y'all work ahead of me, but I'm just going to keep talking through the video. So, 2 more examples. You're welcome to try to beat me to it if you're tuned in still. CaCr2O7. I know it's ionic because I see a polyatomic in there, so it has to be. All right, so just name the parts. Got to be able to find them, though. Ca is calcium. And if I've got good knowledge of my polyatomics, the C2O7 would jump at me. As anybody know what it is? Dichromate. Calcium dichromate. Now, the last one is actually really hard, the RHS2. But I do want to make the point that the moment you have a transition metal start your compound, you are required to show a Roman numeral, right? Unless it's zinc, cadmium, silver, the exceptions. If RH, it's rhodium, if I'm going to write down the name of a transition metal, then I have to make sure that other scientists know which species of rhodium I'm talking about. So, again, it's just this middle area, but rhodium is there. So I have to identify a charge. So RH is rhodium. S is going to be sulfide as the second dude there. And I'm really mean here because a lot of times you can just take whatever number is on the other element and assign it as the Roman numeral, and that usually works. But I made this one really hard. Let's talk about why. Rhodium could have different numbers, but sulfur can only have one number. What is sulfur's charge? It's always 2. But you see what happened here? The 2 didn't cross. The only way a 2 wouldn't cross is if it was reduced with the other number. So this, very sneakily, actually has to be a 4 because that would have chopped them in half to a 2 and a 1, and then the 1 crosses and the 2 crosses. So most of them are not that evil, but it's nice to have an evil one on the video. Man, I was so close to beating that stupid bell. Love you.